Let's look at how alpha, beta and gamma radiation interact with whatever they hit. An alpha particle is like a heavy concrete ball. It interacts very strongly with the ground it rolls over. It's got lots of energy, but it spends that energy in a short distance because it crushes the ground underneath it. A beta particle is like a fast-moving golf ball. It interacts less strongly with the ground as it skips over it. It spends its energy over a long distance because it doesn't damage the ground very much. Gamma radiation is a bit like a breeze. It hardly interacts with the ground at all. It can travel a long distance because it rarely loses any energy. The way that alpha and beta particles lose energy is by ionizing some of the atoms that they pass near. A typical alpha or beta particle will cause several thousand ionizations before it stops. It's the ionizations that cause vapor trails in this cloud chamber. Alpha particles make thick, short vapor trails. The track gets thicker at the end as the alpha slows. This is because it's easier to grab an electron if you're not rushing past. An alpha particle's double positive charge attracts electrons as it flies by. And this is why alpha particles are highly ionizing. Beta particles typically move about 100 times faster than alphas, so they're less good at causing ionizations. And this means they make long, thin tracks of vapor in a cloud chamber. All radiation will go through any material if it's thin enough, and will be stopped by any material if it's thick enough. But to compare penetrating powers, we've traditionally looked at how alpha, beta and gamma fare when presented with air, paper, aluminium and lead. As a rule of thumb, we say that alpha can go through a few centimetres of air, but is stopped by paper. Beta will go through 0.5 millimetre of aluminium, but is stopped by the same thickness of lead. Gamma will go through thin lead, but can be stopped by a couple of centimetres of it. Whereas alpha and beta are either stopped or not stopped, gamma tends to get dimmer as it goes through matter, a bit like light going through lots of sunglasses lenses. It's a common misconception that gamma is so penetrating that it can only be stopped by lead. But any material can stop gamma if it's thick enough. It doesn't need to be strong or airtight. A few metres of straw will cut out 99.999% of gamma. It's just, if we want our shielding to be thin, then we want something dense like lead. Sometimes gamma is less penetrating than visible light. Light happily goes through 50 metres of water, or tens of kilometres of air, but gamma can't. 8 metres of water, or about 1 kilometre of air, is enough to almost completely cut out even the highest energy gamma radiation. And that's why telescopes that look for gamma rays from space have to be in orbit. Most gamma rays can't make it through the atmosphere.